Hello everyone, today we are solving crawling ant problem. The source of this problem is Harvard University Department of Physics. Problem is really challenging, mainly due to mathematical calculation required for the problem. Understanding of two main concepts is required to solve this. First one will be relative motion, that is part of kinematics, and second one is a mathematical tool, linear differential equation, that is part of calculus. Usually in Indian plus 2 syllabus and in IIT preparation, kinematics and relative motion is taught in very beginning and concept of differential equation introduced very late. This could be the reason this problem looks challenging to the student who prepare for IIT or Olympiad. Otherwise, if your calculus is very good, you have like very good exposure of calculus in the beginning itself, in that case the problem won't be very difficult for you. We'll solve this problem in three parts. First part would be analysis part. We'll analyze it properly. In second part, we'll do the like physical concepts involved. Okay, so that would be discussed in the second part. And in third part of the problem, we'll apply the mathematical tool. Okay, that is differential equation. And after conclusion of third part, we'll get the desired solution. So first, let's read the problem. A rubber band with initial length L has one end tied to the wall. At t equal to 0, the other end is pulled away from the wall at speed v. Assume that the rubber band stretches uniformly. At the same time, an ant located at the end, not attached to the wall, begins to crawl towards the wall with speed u relative to the band. Will the ant reach the wall? If so, how much time it will take? Okay, let's start solving this problem. So, given in the problem, a rubber band is pulled, with constant speed v. So we can write extension produced in the rubber band in time t is Vt. Also given initial length of the rubber band equal to L. Now the initial length was L and extension produced was Vt. So length of the rubber band at time t would be equal to L plus Vt. Initial length plus extension produced. Here we need to keep in our mind that different point of the rubber band band will have different velocity. Okay, why exactly that happens? One point of the rubber band is fixed to the wall, that point would be at rest, and other end of the rubber band is moving with velocity v. Okay, and as the rubber band stretches uniformly, we could say that speed will also be uniformly varying over its length. Speed, that is v, uh, at different point would be different, and variation of v over the rubber band, over the length of the rubber band, is uniform. Okay, so what exactly we'll write here: at time t, length of the rubber band is vt, is of course L plus vt, and velocity of end connected to the wall is 0. Velocity of rightmost point is v. Based on these two information, what exactly we can say? We could apply the unitary method to get the velocity of any point, as velocity is linearly distributed over the length. Okay, so what exactly we are writing? Velocity at a distance L plus Vt from left end equal to V. So velocity at unit distance from left end equal to V upon L plus Vt. So velocity at x distance from left end equal to V upon L plus Vt into x. X is variable here which varies from 0 to L plus Vt. So by using this expression we could get the velocity at any point. Now the point is, why we have calculated velocity at a distance x. We have calculated velocity at a distance x because position of ant is variable, and now after this step we are going to assume that position of an ant at any time t is a distance x from the fixed end. We now assume that the position of ant is at a distance x from the fixed end of the rubber band at time t. Okay, so this is our analysis part of the problem. Initial analysis is done now. Now we'll see how exactly physics would be applied here. So let's start the application of physics part. So before that we'll have our diagram again for quick reference, and we'll make slight changes in the diagram. Okay, so we are assuming at time t the ant was at a distance x from the left hand, and at the same moment rubber band was stretched by length bt. By this length rubber band got stretched. Okay, this is the initial position of the ant at t equal to 0. Ant was here, and at t equal to t, ant is at a distance x. We are also assuming that ant is like entire motion is along positive x-axis. Okay, means not positive x-axis, actually entire motion is along x-axis. Rubber band stretches along positive x-axis and ant moves along negative x-axis. Velocity of ant is toward negative x direction, and rubber band stretches along positive x direction. Okay, velocity of ant was given with respect to rubber band. Okay, it was mentioned in the problem also. Okay, so velocity of ant with respect to rubber band is velocity of AR. VAR means velocity of ant with respect to rubber band, that is u minus I cap. Ant is moving towards negative x-axis. Velocity of point of the rubber band where ant is placed at time t. At time t, ant was placed at a distance x. Okay, and that velocity we have already calculated. That will write velocity of rubber band with respect to ground or with respect to earth. So that we have already calculated, and that velocity is v upon L plus Vt into x. V upon L plus Vt into x, and this direction is towards positive x-axis I cap. Okay, now we can calculate velocity of ant with respect to earth by using simple relative velocity formula. Now velocity of ant with respect to earth can be written as velocity of ant with respect to earth is equal to velocity of ant with respect to rubber band plus velocity of rubber band with respect to earth. So this is u minus I cap plus v upon L plus Vt x I cap, or we'll write velocity of ant with respect to earth is v upon L plus Vt x minus u I cap. This we are writing dx upon dt, that should be v upon L plus Vt x minus u. So this is the differential equation what we got. So second part of the problem is again over now. Means we have applied the physics whatever we had to apply. Next part would be solution of this differential equation. This is linear differential equation, and in 12th standard, actually if you are in 12th standard, you must be knowing the solution of this particular thing. And solution is taught like very like very quick solution, like you'll get the AIF integrating factor and multiply it and you will get the solution directly. But like I'm assuming like lot of you is like unaware of the solution of that particular way. So we'll go by very basic, okay, and we'll try to do it by step, okay. So let's start solving the differential equation now. So dx by dt minus v upon L plus Vt into x equal to minus u. So here second term is function of x only. It's like function of x means linear function of x. That's why this is called as linear differential equation. So here we need to calculate IF, integrating factor, okay. The integrating factor or IF would be equal to e raised to integration of minus v upon L plus Vt term with x, okay, dt. This we need to get. So let's do this. So if you integrate it, you'll get e raised to minus v 1 upon L plus Vt dt would be ln L plus Vt upon v. So this is e raised to minus ln L plus Vt. So this is the value of IF, or you can write IF e raised to ln 1 upon L plus Vt. Here you have applied properties of logarithmic function. Minus ln x is ln 1 by x, and one more property will apply here. This could be written as simply 1 by ln 1 upon L plus Vt. How exactly we are writing that? So whenever you have this is L plus Vt, so whenever you have e raised to ln x, that could be directly written as x. So similar way, here you have e raised to ln 1 by L plus Vt, so we have directly written 1 by L plus Vt. Now after getting IF, we just have to multiply with this integrating factor on both the sides. So above equation will become 1 upon L plus Vt dx upon dt minus 1 upon L plus Vt into v by L plus Vt into x equal to minus u upon L plus Vt. Okay, so this is 1 upon L plus Vt dx by dt minus v upon L plus Vt whole square x is minus u upon L plus Vt. This could be written as d by dt of x upon L plus Vt. So if you know the product rule of differentiation and you tried expanding d by dt of x by L plus Vt, you'll get the above things, okay. Now we could also write dx upon L plus Vt is minus u upon L plus Vt dt. Now what? We'll integrate both sides. Integrating both sides. D x upon L plus Vt is equal to, minus u is constant, we can take that out, 1 upon L plus Vt dt. Right hand side, motion was started at t equal to 0 and we are assuming that it ends at t. And left hand side, you have to understand, here we have two variables x and t, and initially x was L, the position of ant was right hand, x is L and t was 0. Finally ant reaches the left hand, so x equal to 0 and t would be equal to t. Okay, integration of dz is simply z, so this become x upon L plus Vt simply. X equal to L and t equal to 0 to x equal to 0 and t equal to t, and here minus u, and this integration would be ln L plus Vt upon V 0 to t. Now we'll put the limit. Initial limit is x is 0, t is t. If you put x equal to 0, entire term would be 0, then a minus sign, and if you put x as L, t as 0, so that will become L upon L, that is 1. Here you have minus u by v ln L plus Vt minus, if you put t equal to 0, it is ln L. So this is minus 1 is minus u upon v and ln L plus Vt minus ln L. Or we could write here v upon u is ln L plus Vt upon L, or L plus Vt upon L is e raised to v upon u. L plus Vt is equal to L e raised to v upon u. Vt would be L e raised to v by u minus 1, or t would be L by v e raised to v by u minus 1. So this is the time taken by ant to reach the left hand, means to reach the wall actually. Now after that, so we got the time. After that, one more question was asked, that was actually first question, will the ant reach the wall? So we'll take two cases here, okay. So first case would be our u is very smaller than v, and second case would be v is very smaller than u, okay. So if u very smaller than v, means ant is moving very slowly and rubber band is expanding very fast. So in that case, v by u would be very greater than 1, or we'll say v by u is very large. If v by u is very large, e raised to v by u is also very large. And if e raised to v by u is large, time taken by ant, that is t, would be very large, okay. So value of t is very high. So in this case, ant will take large amount of time to reach the wall. It's taking large amount of time, but eventually it is reaching the wall, okay. One more case we could have, if v is very lesser than u, means in this case a rubber band is expanding very slowly and ant is moving very fast. In this case, v by u would be very less than 1. If v by u is very less than 1, e raised to v by u is very small. If e raised to v by u is very small, we have like exponential expansion, e raised to x could be written as 1 plus x if x is very less than 1. E raised to v by u in such case could be written as 1 plus v by u simply, and our time was L upon v e raised to v by u minus 1. So t would be L by v 1 plus v by u minus 1. So t in this case is L upon u simply. So this is rubber band is like fixed, it's not expanding, speed is u, distance covered by length ant is L and speed was u, so time would be L by u. In this case ant will reach very quickly. So whatever be the case, a rubber band is reaching the wall for sure. So yes, in every case rubber band will reach the wall. Okay, this analogy also explains the kinematics of expanding universe. It demonstrates that we eventually receive light which is traveling towards us with speed u equal to c, where universe is expanding away from us at a speed v greater than c. We all are knowing that our universe is expanding, and that expansion is not very slow, it's very fast expansion. Okay, so suppose our universe is expanding with a speed which is greater than c, and from the same universe, we are also in same universe, from the same universe, from a particular source, light is traveling towards earth with a speed u which is equal to c. So expansion of universe is similar to your expansion of a rubber band, and the light source moving towards us was similar to ant moving towards the wall. What exactly we have seen? Ant was eventually reaching the wall. So in this case also, speed of light, that is light from the source, will eventually reach us. It will reach us whatever be the rate of expansion of the universe. In every case, light will reach us from any source available in this universe. Yes, the time taken might be very large. Okay, so that is it about this problem. I hope you liked the solution and you understood it well. If you want like solution of any other problem, you can let me know in the comment box. If you want me to discuss any concepts as well, let me know in the comment box, that also can be done. I'm planning to make more videos, but that videos would be based on your interest. If you want like more, if you want particular areas, that area would be covered. Okay, thanks very much.